Reactive and explosive materials. What are they? Where will you find them? And just how destructive can they be? Now, you're watching this presentation presumably because your job does or could bring you in contact with some of these materials. Perhaps it will be under normal or non-hazardous circumstances. Perhaps it will be in response to some emergency. In either case, what you don't know just might kill you. Now, it's not our intention here to show you how to properly store, handle, or neutralize these materials. It is our intention, however, to demonstrate just what some of these relatively common materials are capable of doing. Materials that are routinely used in industry, R&D labs, universities, schools, and hospitals. Materials that are routinely transported over our highways. We hope you'll go away with a better respect for these potentially harmful materials, and we'll go on to learn more specifically how to respond to and safely handle them. A reactive or explosive material is any material capable of a violent or explosive decomposition when subjected to shock, heat, friction, flame, static discharge, elevated temperatures, and sometimes exposure to air or to water. Some materials may become so sensitive that for no apparent reason they may decompose or explode spontaneously. The decomposition may produce a lethal shock wave, or extreme heat, flame, or a gas that itself may ignite or explode. It is very possible that it will produce some combination of all of these. Hazardous materials are divided into classifications according to their characteristics. Most are labeled with these standard industry warnings. Whether the materials are being used, transported, or stored, you should find a placard or warning label posted on the vehicle, the storage area, and sometimes on the material's container or label itself. This is your first clue as to the potential of the material. This is the first clue a safety officer or emergency worker needs when dealing with the material. From the label, you'll have some indication whether the material is likely to burn or explode, whether a resulting fire should be treated with water, or whether water would turn a bad situation into a disaster, whether the material will emit toxic fumes, whether the material needs to be refrigerated. Today, we'll be dealing with reactive and explosive materials that fall into 9 hazard classifications. We will initiate some in a controlled environment to demonstrate their potential. A Class A explosive is a material capable of detonating when subjected to shock or heat. The degree of sensitivity varies greatly from one compound to another. The more stable the compound, the more abuse it can take. The more unstable, the more likely it is to go off with little provocation. This is a commercially manufactured nitroglycerin-based explosive commonly used in rock blasting. It is a relatively stable product and will therefore withstand normal storage and handling safely. It requires a fairly high degree of heat or shock to detonate. Under normal conditions, it behaves very predictably. All things considered, it is a reasonably safe product. When detonated, it releases a high degree of energy. Let's take a look. In our demonstration lab, we've placed about 1 ounce of this explosive on a stand and inserted an electric blasting cap to initiate it. Watch the bottles in the proximity. That was a detonation. A detonation is the extremely rapid and violent decomposition of a material, producing a shock wave, which may be extremely destructive to nearby objects. The speed of sound is 1,250 feet per second. The speed of a detonation, as it moves through the material, is generally from 3,000 to 30,000 feet per second. Very supersonic. This is a characteristic of what is known as high explosives. Picric acid, which you met briefly at the opening of this program, is a typical high explosive. It detonates at 24,000 feet per second, over 16,000 miles per hour. We'll see just how destructive it can be a little later. As a direct result of such a detonation, a high-pressure shock wave radiates outward in all directions. It is this shock wave, with its accompanying overpressure, that causes much of the damage. Here's the destructive overpressure of 1 pound of a high explosive. 10 feet from the explosion, the overpressure will be about 5 pounds per square inch. Now, that's 5 pounds over normal air pressure. It's enough to kill you. At 16 feet, the overpressure has dropped to about 3 pounds, enough to do serious damage to structures. At 40 feet, about 1 pound, enough to break windows. At 250 feet, the pressure, now about 1/10 of a pound, is still enough to break some windows. When the speed of a decomposition is less than 1,250 feet per second, and hence subsonic, it's a deflagration rather than a detonation. A deflagration is a very rapid, often violent decomposition with flame, heat, and large amounts of gas. In other words, very rapid burning. When unconfined, this decomposition is slow enough that a shock wave is not produced. It is this difference, the speed of the decomposition, that separates Class A explosives, which detonate, from Class B. A Class B explosive, by definition, is a chemical compound that generally deflagrates rather than detonates. One whose speed of decomposition is 1,250 feet per second or less. Common examples are the pyrotechnic powders used in fireworks and propellants, like this smokeless gunpowder commonly used in small arms ammunition. Here are a few ounces of smokeless powder under the same conditions as our previous demonstration. Compare the results. Notice that the surrounding glassware didn't suffer as before. Since this deflagration was much slower than the preceding detonation, no shock wave was produced. However, be aware that a deflagrating material is quite capable of producing a violent explosion if confined. The confining material itself is likely to break up and produce a lethal missile hazard. The two materials just demonstrated are commercially manufactured explosives in common daily use. Keep in mind that what you saw was a very small quantity of each. Now, let's move away from the explosives and examine other hazard classes. We'll deal with some of the conditions under which they may initiate and the resulting decomposition. Though they aren't classed as explosives, they are capable of extremely violent reaction. Some are quite capable of detonating under the right conditions. Remember, all these demonstrations are of materials in common use. They represent the potential for accident and injury if not handled properly. A flammable liquid is any liquid material that will ignite easily and burn rapidly with a flash point below 100 degrees Fahrenheit. This is ether. In and of itself, it is highly flammable. However, ether has an additional hidden hazard. It has the nasty habit of forming unstable explosive peroxides as it ages and when it is exposed to air. These peroxides may form under the container's cap. They have been the cause of many laboratory accidents. Let's see what could happen if an unsuspecting technician were to open such a container. These ether peroxides are extremely sensitive to shock, friction, or heat. They may also initiate when simply exposed to light. Triethyl aluminum is also a flammable liquid. Like ether, it too has another and very distinct hazard. It is pyrophoric. A pyrophoric is any material that will spontaneously ignite and burn when exposed to air. Now, what might happen if a bottle of this pyrophoric liquid were to drop and break? I think that pretty much speaks for itself. Never underestimate the destructive potential of these materials. You must maintain a healthy respect at all times. An oxidizer is any material, liquid or solid, that spontaneously evolves, that is, gives off oxygen. It can do this at room temperature or when slightly heated. When a source of fuel is present, it supplies the oxygen needed to support or accelerate the burning of that fuel, often with disastrous consequences. Hydrogen peroxide is a common liquid oxidizer. It is found in industry in concentrations of up to 98%. When it comes into direct contact with an organic material, it may cause that material to ignite and burn, or it may combine with that material to form an explosive compound. Here's what happens when hydrogen peroxide of a moderate strength, 70%, comes in contact with wood. Although this reaction is relatively mild, it is a good example of one of the leading causes of transportation and storage fires involving oxidizing materials. Some oxidizers that have become contaminated or are of very high concentration are capable of detonating. Now, don't rush home and throw out your bottle of drugstore hydrogen peroxide. That stuff is only a 3% concentration and quite safe. Ammonium nitrate is a very common solid oxidizer. It may be used as a nitrate fertilizer and also as a blasting agent. Our assistant has contaminated a few ounces of this material with a common flammable liquid and will initiate it for us. In their original state, that is, properly packaged and stored, these compounds are relatively safe. When the packaging is damaged, as could easily occur in a transportation or storage accident, they can become contaminated. Should this occur, they could assume totally different and quite hazardous characteristics. Organic peroxides may be any liquid or solid organic compound that contains oxygen in its structure. What all this means is that it is both a fuel and an oxidizer. Nasty stuff. Such compounds release their oxygen readily and are capable of violent decomposition. Benzol peroxide is a common solid organic peroxide. It often appears as a mild 10% active ingredient in acne medication. However, in its pure form, it is capable of explosive decomposition. Let's see what could happen to this material from the heat generated by the friction of something as seemingly harmless as unscrewing the cap. Dry benzol peroxide is shock, heat, and friction sensitive. Care must be taken not to subject this material to any initiating source. There is no need, however, to rush home and throw out your son's Zitz cream. Another common hazard of organic peroxides is their tendency to decompose when they get too warm. Terms commonly used to describe this characteristic are SADT, self-accelerating decomposition temperature, or MSST, maximum safe storage temperature. The temperatures vary from material to material. Now, here's an organic peroxide with an SADT well below room temperature. We've removed it from the refrigerator, and it has reached its self-accelerating decomposition temperature. Some organic peroxide liquids simply off-gas vigorously. Some off-gas and burst into flame. Others may explode quite violently. Flammable solids, basically, are any solid materials that will ignite easily and burn rapidly. Some flammable solids may be pyrophoric, that is, spontaneously ignite and burn when exposed to air. Others, when in contact with water, or even moist air, will ignite, explode, or give off a flammable gas that itself could ignite or explode. This is lithium aluminum hydride. It's quite water sensitive. It will ignite and burn violently with an extremely hot flame when in contact with water. Watch. This is sodium metal, and it is one of our natural elements, and in small quantities it is essential to sustain life. Pure sodium is extremely water reactive. Some flammable solids, like the sodium, are water reactive, while others, like this white phosphorus, are sensitive to air. While sodium must be kept dry, white phosphorus must be stored underwater. It will ignite quite rapidly when exposed to air. That was a mild reaction of an air-sensitive flammable solid. Let's try something a little more energetic. Picric acid, technically trinitrophenol, is a relatively stable explosive, much like its brother, trinitrotoluene, TNT. Picric acid is shipped as a flammable solid when wet with 10% or more of water. Over time, however, it can dry out and, if contaminated, become a very sensitive explosive. Contaminated picric acid may form picrate salts. These very unstable salts, much like the peroxide that forms in ether, may cause the entire bottle to detonate. Here's what's very likely to happen if a jar of picric acid with picrate salt under the cap is opened by an unsuspecting technician. Clearly, these materials can be deadly and should never be underestimated. You should be aware that all the beakers, flasks, and bottles displayed in our mock laboratory, except the one we were demonstrating, contain inert materials. Were this a real situation in a lab with live materials, they could only increase the hazard. What you have seen demonstrated could be much worse. There is one more thing I'd like to discuss before we conclude. These are typical steel cylinders. They could contain just about anything: a compressed gas, a liquefied gas, or a liquid. The contents may or may not be flammable. The point is, cylinders are often poorly or inaccurately marked. Sometimes they lack any marking at all. The contents may be a strong oxidizer, or very corrosive, or toxic. They may be air reactive, flammable, or pyrophoric. With any cylinder, we must understand the characteristics and the physical state of its contents. If the contents are unknown, an analysis sample must be taken by an experienced technician. All cylinders must be handled with care. In addition to the hazard of the material, there's a serious high-pressure hazard as well. Cylinders must be protected against the uncontrolled release of pressure that may be as high as 6,000 pounds per square inch. Let's rupture and ignite this cylinder of flammable gas. We have demonstrated some of the hazardous characteristics of materials that may typically be found in the workplace. We've observed samples of both A and B explosives, flammable liquids and solids, water-reactive solids, organic peroxides, oxidizers, and flammable gases. We hope we've been successful in getting your attention, and that you now better understand the harmful potential of these reactive and explosive materials. Remember, the materials used in these demonstrations are but a few of the many found in common use today. In order to safely handle them, control them, and neutralize them, we must understand the characteristics of each and every material that we may come in contact with. Does a material detonate or deflagrate? Does it cause, support, or accelerate combustion? Does it release a flammable gas or just burn quietly after self-ignition? The quantity of material must also be considered so proper safety distance can be maintained. We must understand the stimulus that may cause a decomposition. We must also understand why and how a material may become sensitized to an initiating stimulus. Always research a material thoroughly before handling it to better understand its characteristics. Be especially cautious with unknown materials, old containers, and illegible labels. This may be the one that kills you. This is the first of several video productions dealing with reactive and explosive materials. We hope you will take the opportunity to join us again and examine in more detail the safe handling, storage, and neutralization of such materials. I'd like to leave you with this thought in mind.